Hi everyone. So as I said in the end of last lecture, we have a few more remarks I want to make about the business of global Wellposedness for the semi-linear Klein-Gordon wave equation. So let me just get those over very quickly. There'll be a little bit less proof today, but I just want to sort of this lecture will be more of a show and tell and less of a proof. I just want to sort of give you some ideas of what things can happen. So as I said earlier, that we have we proved the global Wellposedness theorem for general nonlinearities for both the nonlinear wave equation and nonlinear Klein-Gordon equations when the spatial dimension is d bigger than or equal to 4. Now, and we were able to also discuss how if we assume sort of non-generic nonlinearities which are cubic or quartic instead of the generic quadratic nonlinearities, we can extend these down to dimension d equal to 3, dimension d equal to 2, by taking advantage of the fact that the nonlinearity, when stacked on top of each other, when you have cubic nonlinearities, then you're going to have a overall faster decay rate because you have two decaying factors, to play with instead of just one. It turns out that also there's another thing that's not sharp about our argument in the global Wellposedness statement for the Klein-Gordon case. And that is, remember like way back here when we talked about the estimate. So when we started estimating the inhomogeneity in our argument, where was it? This would be over here, right? Over here, remember that in this part where we talked about the L2 integral estimates for the L derivatives acting on inhomogeneity, how we, on the right hand side, we plug in H evaluated at this energy quantity multiplied by the decaying factor T1 minus D over 2, and where do we get this T to the power 1 minus D over 2? This is because we have the pointwise estimates that we established earlier for low derivatives of the input phi, right, measuring out infinity, being bounded by higher derivatives measured in these energy flux spaces relative to the hyperboloid. Okay, and we have this decaying factor coming out in front of it. And one of the things we mentioned was this, that for the Klein-Gordon equation, in principle, we can get a better decay. In principle, we can get T to the power D over 2, right? It's just only for convenience, and because we could, we replace it using the slightly worse decay, T to the power D minus 1 over 2. Okay, for just to put the two discussions, both the wave equation and Klein-Gordon equation, together. Now, if we isolate out the Klein-Gordon equation, then we can ask, wait a second, we can actually get a decay rate of T to D over 2 instead of D minus 1 over 2. Then can we not take advantage of this D over 2 and get better global Wellposedness statement? In particular, if things decay at T to the power D over 2 instead of D minus 1 over 2, then at 3 dimensions, this will be T to the negative 3 halves, which will be integrable. And T to the minus 3 halves will give you that in 3 dimensions, you actually have global Wellposedness small data for generic nonlinearities for nonlinear Klein-Gordon equation. And it turns out the answer is yes. That you can actually do that. You can accomplish that statement. However, the proof that I've given above does not factor through directly. And I'm going to explain very quickly why the proof doesn't work and how we can modify the proof to make it work. But this will be done very quickly and sort of very sketchily. And if you have time, if you're interested, I welcome you to try to reproduce the proof based on what I'll be talking about and based on what has been given in fairly good detail above for the generic case. Okay, so the theorem is that small data global Wellposedness also hold if I know that box M phi equal to F phi and D phi with M positive when D is equal to 3, okay? And however, here we're going to be using, instead of D plus 2 derivative, so remember previously we required a sufficiently smallness being phi naught measured in HD plus 2 being sufficiently small, and phi 1 measured in HD plus 1 being sufficiently small. Here we're going to require that phi naught is measured in HD plus 3, and phi 1 is measured in HD plus 2. Okay. Now the key idea really is that we can get Klein-Gordon to decay like T to the minus D over 2 if we use one more derivative. Okay. And this means that particularly this means that for derivative terms. However, there's a sort of small problem because if we look at a pointwise estimate, right? If we go back to the pointwise estimate, we cannot actually, based on the kind of spaces that we used, based on the E space and the curly E spaces, we cannot estimate the pointwise estimate for derivatives of the solution to the Klein-Gordon equation with decay rate t to the d minus 2. It's because that the energy, right, the energy does not control things that look like straight up derivatives. If you look at the curly E energy, this does not control things that look like straight up normal partial differential of phi. It controls only this funny L derivatives and some factors of d by dt. So in order to actually recover these types of to recover the decay for things that looks like normal partial derivatives of phi, what we need to do is we need to actually enlarge our function space. Actually, instead of using this curly E and the and rectangular E as we did before, our function spaces now have to actually incorporate both L derivatives and normal partial derivatives. Okay? So in other words, what we need to do is replace EK and EK by spaces where the K derivatives can be either a Lorentz boost L or a partial differential operator. So we're going to allow something like L, L, partial, partial, L, partial, L acting on phi. Something like this. Okay, and what we're going to try to so by incorporating both partials and L's, what we're going to do is that we're going to be able to say that the partial differentials are going to also be bounded sufficiently by the energy. Okay, because now we allow there to be partial derivatives on phi itself. Okay, so this is going to be a sort of this is going to be a technical modification to the argument before, and sort of most of the things are going to be the same. You just have to keep track of the fact that you have to worry not only about L derivatives but also partial derivatives and make everything fit together in exactly the right way. Okay, so and basically just because that just the incorporation of deltas in the partials here really is because the nonlinearity depends on partials of phi, and if we want partials of phi to be decaying like t to the minus d over 2, we have to be able to make that part of the energy that we control. Okay. So anyway, so that's just a technical detail, but with that argument put in, you can actually complete the argument and say that in 3 dimensions, quadratic nonlinearities, by using one more derivative, which is required, we can actually control that we get small data global Wellposedness for the semi-linear Klein-Gordon equation for generic nonlinearities, generic smooth nonlinearities. Okay, so that's the first remark I want to make, which is that you can make use of the improved decay for Klein-Gordon. It's going to you just need to do things a little bit with a little bit more technicality involved. Okay, but it's not out of the realm of possibility. Excuse me. Okay, so the second thing I want to mention in this case is that for generic nonlinearity, we're only able to let's limit ourselves to the wave equation case. Oh, right, for the Klein-Gordon equation, we also see that in 2 dimensions you can work with cubic nonlinearities, and by extension, in 1 dimension you can work with coordinate nonlinearities, and you'll still be able to prove global Wellposedness. Okay, so but okay, let's go back to the but I want to mention the fact that in this low dimensional case, the non-genericity of the nonlinearity that's admissible is actually not just a failure of our technique. It's actually that the corresponding statement is false. So I want to say that So in this final section, I want to mention the fact that when d is less than or equal to 3, and you look at a wave equation, and you look at a generic quadratic nonlinearity, right? Generically, for generic quadratic nonlinearity, it's possible that small data global well-posedness is in fact false. In fact, you do not have small data global well-posedness. That there exists small, compactly supported initial data that for which the solution is going to become singular in finite time. That you cannot solve it globally in time. So let me just sort of give you a very quick sketch of the argument of how this works. Okay. So we're going to consider the following generic quadratic nonlinear semi-linear wave equation in d equal to 3. Okay. So we're going to solve box phi. So this will be a wave operator equal to dt phi squared. Okay. So what we're going to do is we're going to actually reduce this essentially to an argument by method of characteristics. So we're going to assume that phi is a rotational symmetric function. So phi only depends on the radius distance from the origin. And we're going to set eta to be equal to r times phi, just for convenience. Now, one of the things that we notice is that in 3 dimensions is a magical computation where the box operator in 3 dimensions actually, if you look at the polar coordinate system, can be written as 1 over r dt plus dr acting on dt minus dr acting on eta. Okay, so this is equal to box phi. So this is your computation. You can check it yourself. And actually, I think if you took PDE 1 with me, then you have seen this actually done when we talked about the wave equation. But okay, so let's look at the equation for eta. So we know if phi were a solution to box phi equal to dt phi squared, right? What equation must eta satisfied? Well, so box phi is, as I said, 1 over r dt plus dr, dt minus dr acting on eta. And the right-hand side, right? Right-hand side, dt phi, right, is 1 over r dt of eta, right? And dt of eta can be written as 1 half dt plus dr and 1 half dt minus dr. So I can write it as 1 over r squared, right, from 2 factors, times 1 and the average of dt plus dr eta and dt minus dr eta quantity squared. Now we're going to choose a very, okay, so why do I write it in this funny way using dt plus dr and dt minus dr? The reason is because if I write it in this way, I can choose a well-supported initial data to make one of the two terms go to 0. So if you look at phi naught, right, so in my initial data, I choose an arbitrary initial data phi naught that's supported on the annulus where r is between 1 and 2. Okay? Now I'm going to choose my phi 1 in a funny way. I'm going to choose phi 1 so that phi 1 is equal to minus 1 over r times the radial derivative of r phi naught. Okay? That can be done. Phi naught is some radial function. We should choose phi 1 to be such, another radial function. And because that phi naught is supported away from r equal to 0, right, phi 1 is still going to be, so if phi naught is, let's say, smooth and completely supported, phi 1 is still smooth and completely supported because the support is away from where 1 over r is singular. Okay? So this is also supported on r between 1 and 2. And one interesting thing is that if you look at the initial data for eta, dt plus dr acting on eta evaluated t equal to 0 based on my choice of phi naught and phi 1, this is chosen exactly so that dt plus dr eta is going to be 0. Okay. All right. And so one can make some sort of finite speed propagation argument, which I'm not going to make precise here, but one can actually say the following is true. Based on this, we actually know the following. We actually know that let's see, how do I address this in the proper way? Right. So actually, the easiest way to say is just the following. It's just that so because we know dt plus dr eta is going to be 0, we can sort of for first pass we can pretend that dt plus dr eta is actually more or less 0. Okay. So throughout the solution, of course, this is not going to be true. It's sort of because the equation is nonlinear, that we are going to have that dt plus dr is going to become non-zero at some later time. But let's pretend for a second that dt plus dr is 0, because that thing is going to be comparatively smaller to the dt minus dr term, and we can like things the schematic argument that we're going to write below can actually be made rigorous. But let's just pretend for a second that we can actually, because of this prescription on data, we can pretend that dt plus dr eta is actually going to be vanishing for the entire solution. Pretend for now, okay? If that were the case, right, then we can write the equation essentially as an ODE, right? The equation saying dt plus dr eta is going to be 0. This term goes away, and we have only dt minus dr eta quantity squared. Okay, so the ODE satisfied by dt minus dr eta, the quantity dt minus dr eta, satisfied ODE, which is dt plus dr. This is a derivative in the dt plus dr direction, is equal to 1 over 4r dt minus dr eta itself squared. Right, so this is an ODE for dt minus dr, and you can solve it. Right, this is a very simple ODE. You can actually solve that. This tells you that 1 minus quantity dt minus dr eta minus 1 over dt minus dr eta, right, at the initial value, is equal to 1/4 the natural log of r plus s over r. This is just this is just the solving the ODE. Okay. All right. So what is the upshot? Right. The upshot is that because we have this equation here, right? The equation satisfied by the quantity dt minus dr eta is essentially a Riccati equation, right? You have a your derivative equal to something squared. And so we know it's well known that Riccati equations for initial data with the correct sign is going to blow up in finite time. So in particular, if you know that dt minus dr eta at time t equal to 0, right, at location r, is such that it could less than 0. So under our assumption, this actually tells us that dt minus dr eta at some positive s, so some positive time s, at location r plus s, this is going to become infinity. Right, because we have this term is negative, right? This term is negative. So we have that this term is equal to what? It's equal to this term, which is a positive number, r plus s is going to be bigger than r, plus something that's negative, right? When s is equal to 0, this is natural log of 1, so this goes to 0. So for some positive s, this is going to increase and make this whole thing 0. But if 1 over something is 0, this tells us this thing over here is actually going to blow up to infinity. Right, so we have dt minus dr eta at evaluated s r plus s is actually going to be infinity for some finite s, and this tells you that, and this only depends on eta having a sign. It does not depend on it does not depend on the normal eta. You can make eta arbitrarily small by multiplying eta by some constant epsilon, right? By making it as small as you want, but it will not change the fact that eta has the wrong sign at the point 0r. And this will tell you that in the future, then this wrong sign will generate a infinity to show up in the solution to a nonlinear equation, and therefore this contradicts the possibility of having a global solution to the semi-linear equation. All right. So, upshot of all this is that, in fact, when dimension d is less than or equal to 3, you try to solve the wave equation for the semi-linear wave equation for generic nonlinearity, quadratic nonlinearity, right? Then it is very possible, in fact, generically true, that the solution does there exists arbitrarily small initial data for which the solution does not exist for all time. Okay, and so we do not have global Wellposedness for such partial differential equations. And the difficulty that we run into where we do not have enough dispersive decay to make the energy argument work, right, is actually reflecting something very fundamental, the fact that it does not have a global Wellposedness result. It's not just a weakness of the argument, it's just a fact of life. Okay, all right, so with this, we've completed our discussion of the semi-linear wave and coordinate equations, at least the global Wellposedness portions of this. I may revisit this a little later. I'm not quite sure if we have time for that, but the next portion of the course, we're going to be starting to talk about actually the frequency restricted dispersive estimates for the wave and coordinate equations. We're going to sort of upgrade the linear dispersive equations that we proven earlier, right, into a form that we can actually use to prove things like Strickhart's estimates for wave and coordinate equations. All right, with that, see you next time.